product law, or the product rule of differentiation, I should say, is a rule that allows us to differentiate a function that's a product of two other functions. Okay? So let's suppose that we have f of x with a capital F, there we go, is equal to f of x times g of x. Okay? What the product law tells us is this. Big capital F. F prime of x is equal to little f prime of x times g of x plus f of x times g prime of x. Okay, now this is a lot of function notation here. So the way that I remember it is this way. If f of x equals u times v, and u and v are the two different functions, then f prime of x equals u prime v plus u v prime. Okay, so what I'd like to do, yes, say that again? To be honest, I can't remember because I don't know. This is used so often. Here's the answer. You want to know the answer to this? You will use this so frequently that you will not need to look it up. Yeah, that's the answer. Okay? Okay. Sorry, say that again? No. Yes, but not necessarily. I won't always do that. Like, I can't remember if this, I have to look up where's my formula. I have one copy of the formula. You guys take it out. You all have copies. I don't know where it is. I can't remember. Is it on? No, it's not. Yeah, no, I won't give you this. I will not give you this. But you will use it so often that you will not need it. Okay, so let's practice using this once. And then I want to show you why it works. Okay? Because right now I've just given you something that has dropped from the sky. Okay? Now I'm going to show you the proof. You are not responsible for the proof. Okay? So here we have f of x equals x times 3x squared minus 2. Now, by the way, we solved this yesterday by expanding. Okay? So actually, let's do that first. Through expansion, f of x is equal to x times 3x squared is 3x cubed minus 2x. Yes? Okay, so we can figure out the derivative this way. F prime of x is going to equal 3 times 3 is 9x squared minus 2. So, okay, we already know what the derivative is because we could do this one through expansion. Okay, let's find the derivative also using the product rule for differentiation. Okay, so what we're going to do is we're going to say one of these two factors, because the product is x times 3x minus 2. So one of the two factors is going to be u, the other one's going to be v. And I like to kind of do that off to the side. So u equals x, v equals 3x squared minus 2. Okay? If u is x, what would u prime be? 1. And if v is 3x squared minus 2, what would v prime be? Six x. Okay, so according to the product rule, f prime of x is equal to u prime v plus u v prime. Now we've got expressions for all of these, so we're going to plug them in. U is x, v is 3x squared minus 2, plus u, which is x, times v prime, times 6x. Okay, and we're going to expand this all out. So we got x times 3x squared is 3x cubed minus 2x. X times 2 is 2x. Plus x times 6x is 6x. Did I mess? Oh, this should be 6x. No, that's right. Right?
It's one instead of x in the first term.
What did I mess up? Oh, u prime. Ah, that's right. Thank you. Ha. What would I do without you guys? Okay. Remember yesterday I said I stopped making careless mistakes when I was 20? I guess I was wrong. Okay. Right. So u prime is 1 times 3x squared minus 2 plus x times 6x. Right. So now we get 3x squared minus 2 plus 6x squared. And that is the same as that, 9x squared minus 2. Okay, so f prime of x is 9x squared minus 2. Okay, so it's the same. Now, for this particular example, which way do you think is easier? Yeah, expansion, for sure. Yeah, expansion's personal. I mean, listen, you can pick your own method. So if you think using the product rule is easier, pick that. That's fine, okay? I personally think expansion's easier. So you can do things both ways. What we're going to find, though, a little later on in the course, is that we may have some functions that are the product of two separate functions where we can't use the product rule even after we expand. So for example, if I had something where f of x equals x squared times sine x, okay? We haven't looked at derivatives of trigonometric functions yet, but I can't use the product rule there. I'm going to have a problem, right? Or not the product rule, I'm sorry, the power rule, right? If I expand that, I'm still going to have x squared times sine x, but I have to use this rule to be able to differentiate that. Does that make sense? Okay. So what I'd like to do now is I'm just going to go on to another page and show you where this comes from. Well, you can see how it works, like it's true for this particular example, right? It works in this example. We can do it again. This one we can also show both ways, because in this example we can also expand. And we can say, yeah, if we do it this way, if we use the product rule, it works. If we expand, we probably get the same answer. So we can show for specific cases that we'll get the same derivative both ways, okay? But that's not, in mathematics, a rigorous proof. A rigorous proof is when you show that something works in all cases. Okay, so I want to show that to you now, but you are not responsible for this. Okay, but you will see this kind of thing when you take calculus in university. And I like to show it because, again, I, as much as possible, don't like to just drop things from the sky and be like, use it, and it works. I want to show you why. Okay, and we have enough knowledge from what we've done so far to understand why it works. It all comes from limits, right? And it comes from how we get derivatives in the first place. Okay, so why? Well, if f of x equals f of x times g of x. You know what? I'm changing my mind. I'm going to use a different letter here. Is that okay? Because I don't want to confuse things. Is that okay? Let's use a regular old f there and make that an h. Is that okay? Then it's super crystal clear. I'm not using the same letter twice. We don't have to worry about capital letters and lowercase letters. Yeah? Okay. So f prime of x is equal to the limit as, oh shoot, I did it again. Okay, give me another letter, you guys. I know, but now I have to use the limit as h approaches 0. R. Sure, my first name starts with an R. R of x times g of x. There we go. Now there's no h's involved except for this one. The limit as h approaches 0 of r of x plus h times g of x plus h minus r of x times g of x over h. Does that look familiar? Yep. Okay, good. This is how we get the derivative of any function, right? Now what we saw when we looked at the power rule is that when we have functions that look a particular way, like for example, we can write functions as x to a specific power, their derivatives will always look the same, right? That's the power rule, and that speeds things up a little bit. But where does that all come from? It comes from here. Okay, so I'm going back to sort of the basics. Okay, so now what I'm going to do is I'm going to add and subtract the same term in here. And if I add and subtract the same term, what I'm actually doing is I'm adding and subtracting 0 minus r of x plus h times g of x plus r of x plus h times g of x minus r of x times g of x over h. Okay, so what I did there is I still have this. Oh no, sorry. Plus, I messed that up. This should be g of x plus h. So this is the same as that. This is the same as this last term here, even though I wrote it really squishy. And then in the middle, I've taken this term, r of x plus h times g of h, and I subtracted and added the exact same thing, which means I've added 0. Okay? So although it looks like I've made things more complicated, this second line is equal to the above line because all I've done is I've added 0. I add and subtract the same thing. I've added 0. Okay? Now, though, what I have is in these first two terms, I've got a common factor of r of x plus h. And in these last two terms, I've got a common factor of g of x. And so I'm going to factor that out. Let's see if I can make this a little squishier so it doesn't, or not spread out as much at the beginning so that things don't get so squishy at the end. So in these first two terms, I have this common factor of r of x plus h. So I'm going to factor that out. And what's left is g of x minus, or g of x plus h minus g of x. Okay, so that's this piece. So far, so good? And if you guys just want to watch and not write down, that's okay, because you're not responsible for this. I just want you guys to know where it comes from. Okay? So that's these two terms. Now in these two terms, my common factor is g of x. So I'm going to factor that out. Okay? Plus g of x times, now what's left from here is r of x plus h minus r of x. All over h. So all I've done is it's like factoring by parts, right? I factored the first two terms, GCF out of the first two terms, factor GCF out of the last two terms. So far, so good? Okay. So now what I'm going to do is I'm going to split this up into two different fractions. And in fact, into two different limits. I'll spread it up into this limit plus this limit. So this one is r of x plus h times g of x plus h minus g of x over h. Whoops, I forgot a bracket there. So that's this part plus the limit as h approaches 0 of g of x times r of x plus h minus r of x over h. In fact, at this point, I don't even need those big brackets around there, but oh well. Okay, so now I've split it up into two different limits. It's like I'm splitting it up into two different fractions over h. So far, so good? Some of you are like not nodding along anymore. No? Where did I lose you? Yes, no? You're like, get on with it, so we keep going, okay? Okay, and now what I'm gonna do is I'm gonna I can multiply r of x plus h times this, and g of x plus h times that. So I'm gonna break that up even further. So I'm gonna write this as the limit, as h approaches 0, of r of x plus h times the limit as h approaches 0 of this piece, of g of x plus h minus g of x over h plus the limit as h approaches 0 of g of x times the limit as h approaches 0 of r of x plus h minus r of x over h. Okay, because basically this piece is r of x plus h times this fraction. So now I'm breaking it up into the product of two limits. Yeah?
Why isn't rx plus h over h?
Okay, why? Because then, if you think about it, if this was also over h, if you multiplied those together again, the denominator would now be h squared, going the other way, right? So this is like over 1. Does that make sense? Okay. All right, now what we can do is here, we can plug in a 0 for h, because there's no h in the denominator here. So if I plug in a 0 for h, I'm just going to get r of x plus 0, which is fine, times, well, this is g prime of x. Plus this, there's no h in here at all. So I can just write this as g of x times, this is now r prime of x. And so what I get is that f prime of x is equal to, this becomes r of x plus 0 is just r of x times g prime of x plus g of x times r prime of x, which is the product rule. Okay, I think when I did my algebra, the order of my terms seemed to got reversed from the one I gave you. But it doesn't matter because it's addition, right? So where does this come from? It comes from the way that we derive the way that we come up with any derivative. Okay? You're not responsible for this. But the reason why I wanted to show you this is that a lot of stuff that we're going to do with derivatives is based on this. So I wanted to show you the proof of this so that when we do all that other stuff and I'm like, oh, it's because of the product law, you can see the original derivation and the original proof. Okay? Now let's just talk about how to use it. Did Isaac Newton come up with all of this stuff? Yes, he did. He and Leibniz, what's his name? Leibniz? There's a bunch of people who are credited with coming up with calculus. He's probably the most famous, but he's not the only one. And to be honest, I don't know enough about the history, or I don't remember enough about the history to answer who came up with each part. But there's a lot of different theorems that we're going to look at. And I'll tell you what, I'll do my homework on that, and I'll tell you more about it on Monday, okay? Specifically with the stuff that we're learning, because I like that kind of stuff too, so I'm happy to do homework on that, okay? Now let's just practice using this thing, okay? Because like the stuff that we're going to do here, by the way, today, because we haven't learned about derivatives of other types of functions, right? All we've learned about so far is that power rule. Basically, everything that we're going to do could be done through expansion, okay? So the fact that we're using the product law today is just an option. But as soon as we bring in other types of functions, like exponential functions, logarithmic functions. Radical functions can be written with a power, so that falls into the category of power rule. Radical functions, exponential functions, trigonometric functions, all of those types of things, we have to use the product law, okay? Okay, so this guy over here, again, we could try and do it using expansion as well, but let's start by using the product law. So if we're using the product law, you want to call one of them U and one of them V. And again, because you're multiplying, order doesn't matter, so it doesn't really matter which one is which. So if U equals x cubed plus 3, and actually, I'll leave some space. V equals 1 minus 2x. Okay. We also need to come up with U prime and V prime. Okay? So here u prime would be 3x squared, and this guy, v prime, negative 2. Okay? So I'm going to call this, let's switch this to y equals x cubed plus 3 times 1 minus 2x, so that instead of writing d of all of that by dx, I can just write dy by dx, because that's shorter. This is going to be u prime v plus u v prime. And I have all of the components written on the right. Okay, and of course, when I derived it, these were in the opposite order. Again, it doesn't matter because addition, when you're adding two things, 2 plus 3 is the same as 3 plus 2. Okay, so if you wrote it as uv prime plus u prime v, that's fine too. This is, u prime is 3x squared times v is 1 minus 2x plus, oh, I'm not leaving myself a lot of room here, u is x cubed plus 3 times v prime is negative 2. Okay, and then we just need to expand. So this is going to be 3x squared and then minus 6x cubed, and then minus 2x cubed, and then minus 6. So all together, that is negative 8x cubed plus 3x squared minus 6. Okay, now of course you can do this through expansion as well if you want. So we can just check that. If y equals x cubed plus 3 times 1 minus 2x, we're going to get x cubed minus, what is that, 2x to the 4 plus 3, and then minus 6x. Minus 6. I'm getting really squishy here. Okay, I'm going to squish this in a little bit more. Okay, so let's do that again. So plus 3 minus 6x. So if I expanded, that's what I would get. And then I just use my power rule. And I get here, this is going to become 2x squared. This is going to become minus 8x cubed. This is just 0, and then minus 6. Oh, sorry, this should be 3x squared. There we go, 3x squared. Okay, so we get the same thing. Okay, now for this example, although we could expand here, it's a bit of a pain in the butt to expand these these terms with rational exponents. So this might be nicer to do using the product law, the product rule. I keep saying the product law. Product law is for exponents and for logs, right? Product rule of differentiation. Okay, so again, one of them's u, one of them's v. And here you would want to write this as 6x to the 1/2. Right? V is 2x cubed plus 3x minus 9. And then we can find the derivatives of each of those parts. So u prime is going to be 6 times a half x to the negative a half. And v prime is 3 times 2 is 6x squared plus 3. Okay, so dy by dx equals u prime v plus u v prime. And u prime v is this guy. Oh, and that, by the way, is 3x to the negative 1/2. Now, you could write that as 3 over the square root of x, right? But, and you might do that at first, right? Because you guys are a little bit inexperienced. But what you're going to see eventually is that if we do that, you'll be like, oh, you know what, though? I have to multiply that by v. And so I'm going to have to use exponent laws anyway. And so if I put it into radical form right now, I'm going to have to take it out of radical form anyway, right? So if you make that mistake, it's not a mistake, but if you go and put this derivative for u prime into radical form, right, or even just make the exponent positive at this stage, that's okay. Just once you realize, oh, I have to expand, make it back into a negative exponent, so that when you distribute, you can add the exponents together, right? So this is going to become 3x to the negative 1/2 times v is 2x cubed plus 3x minus 9 plus, I'm running out of space, u is, again, I'm going to use this version of 6x to the 1/2 because I've got to multiply it by v prime. So I'm going to be doing distribution there. So 6x to the 1/2 times 6x squared plus 3. Okay, and now I can add the exponents together, right? So 3 times 2 is 6. I got to do all this distribution. And then x to the 1/2 times x cubed is x to the 2.5, or 5 over 2, right? And then 3 times 3 is 9. And x to the 1/2 times x to the 1, so a half times 1, or sorry, a half plus 1, or negative, oh my gosh, what's happening? It's Friday afternoon. Ugh, negative a half plus 1 is half. There we go. And then 9 times 3 is 27, x to the negative 1/2. There we go. 3 times 9. Did I say 9 times 9? Okay, I did say 9 times 9, but I was obviously thinking 3 times 9 because that's what I put on the board. Whew, at least one part of my brain is working, the part that controls my hand. Okay. Then we have to do this piece. And we're going to go 6 times 6 is 36. And x to the 1/2 times x squared, well, half plus 2 is 2.5, so, and 6 times 3 is 18, there we go, and x to the 1/2. Whew. And so what are we going to have here? Well, we got some like terms. That's nice. So we've got 6x to the 2.5 plus 36x to the 2.5, so 42x to the 2.5. And then 9 plus 18 is plus 27x to the 1/2 minus 27x to the negative 1/2. Okay, and then we can go ahead and put this stuff into radical form. I would at least make this exponent positive. Okay, if you want to leave them in in exponential form with rational exponents, that's fine, but make this guy positive. But I'm just going to show you, just as a review, how to do that. So this is 2.5, by the way, is 5 over 2, right? So this is going to be 42 times the square root of x to the 5 plus 27 times the square root of x, and then minus 27 over the square root of x. And that was, what notation? It was dy dx. The notation was dy dx. Okay, what would be a good way to check your work? Expand, yes. I'm not going to do that now because I think that I've done enough damage for today, and yeah, let's just move on. But you guys can do that. Okay, so this is a question that is similar to one that we've seen many times. Find the slope of the tangent line to the graph of f of x at the point 128. Okay, so this is a point on the graph. If we plug a 1 in for x, we should get 28 because we're going to get 5 times 1 squared minus 1 times 4 times 1 cubed plus 3, and that is 4 times 7, which is 28. Okay, so that's where the point 128 comes from. Okay, now to get the slope, what would we need? Say that again? The derivative, yes. Now that we have the ability to find derivatives, that's the easiest way to get the slope. We can find the derivative of the function and find the value of the derivative when x equals 1. Okay, so let's practice using the product law, although we could expand this one as well. We've just learned the product rule. At some point this semester, maybe I'll stop saying law and start saying rule. So let's practice that. So f of x equals 5x squared minus 1 times 4x cubed plus 3. So let's say u equals 5x squared minus 1 and v equals 4x cubed plus 3. Okay. What is u prime? And what's v prime? What's u prime? Yep. Yes. And v prime? 12x squared. Yeah. So f prime of x is u prime v plus u v prime. I always write this out because it helps me to remember where to put all of these different pieces. Well, you don't have to. So that's 10x times 4x cubed plus 3 plus 5x minus 1, 5x squared minus 1 times 12x squared. Okay, now let me ask you a question. If I asked you for the derivative, I would expect you to expand, simplify, collect like terms, right? I just asked for the slope of the tangent line at that point. Do you need to expand and simplify and collect like terms to find the slope of the tangent line at that point? No, what could we do right now? Plug in a 1, yeah. And particularly since it's a 1, 1 is a very easy number to plug into a function. So sure, you could expand and simplify. You guys have lots of practice doing that. But to answer this specific question, you actually don't need to take that step. you just need to plug in f prime of 1 is 10 times 1 plus 4 times 1 cubed plus 3 plus 5 times 1 squared minus 1 times 12 times 1 squared. It's a very, very easy number to plug in, right? And that is 10 times 7 plus, this is 4 times 12. So take that extra, slow down a little bit and make sure you're reading the instructions. And, it's no problem to expand and simplify and then plug in 1 at the end, but you don't always need to. And actually, some people make mistakes in that expansion process, and then their answer at the end of the day is wrong. And if they had just plugged in a 1 right initially, then they may not have gotten the wrong answer, right? So that's 70 plus 48, which is 118. So the slope of the tangent to f of x at 128 is 118. Okay, we're good so far? I think that's all I have for you guys today. We're going to call it a day. We'll talk about the quotient rule on Monday. And luckily, the quotient rule is derived from the product rule. So we're basically going to take the product rule and rearrange the terms to get the quotient rule. The derivation takes about 30 seconds. Okay, so that one will be a lot simpler. But we had to go through the pain today to get to what we'll be able to do on Monday.